Greeting. I'm Gordon Neal, and I'm the instructor of mathematics at the Arch Education. Right before I worked at Arch, I worked at the university for 3 years, and I was in charge of the university courses at the time. So I have students with their tutorial, with their tutorial homework. I grade their examinations, and I also hold the grade book, right? So that's what I did at the college level. And moreover, before I joined the university, I also get awarded in the list and also the academic honor list during my study in basically every semester. So you can say that I'm quite experienced. I'm quite experienced teacher in mathematics in general. I pick integration because integration is actually very common in both syllabus, and the technique required is actually quite high. You need really good mathematics sense and ideas before you can handle integration. So that's why I pick integration. And also this question is involving substitution. If you're good at, you know what a substitution is. So substitution is actually a very common uh technique, right, in both A and AI, which is quite common. Of course, right, if you need to do integration by parts, right, that will be in a certain syllabus, but not in the others, right. So that's why I don't pick question in by doing by parts there. If you know what I mean, right, that's quite technical integration by parts, right. So now let's start, right. Why don't we just start, right, with our like solution here? The question is quite generous. They teach us, right, to use a substitution by u equals sine x, right? So we just start with it, right? So we just let u equals sine x, right? And then we just start with if you know the technique in substitution, you know that we need to differentiate. Let's do du dx, which is cosine x, right? So in other words, right, we know that du is actually cosine x dx, right? So we change the subject. So now um the objective, right, of integration by substitution is that we would like to make sure that we change the subject from x to u. That's our focus, right? So now let's change the color to black. Okay, so we just use integration, and then the sine x, right? So we just replace the sine x with u. That's what they teach, right? U. So and then isn't it familiar? So cosine x dx, right, is what we see here. It's actually du. So u du, and for the bottom, right, we can turn it to u squared. Just replace every size with u, right? So that's what they teach us to do. And then so we can see that we turn it from a trigonometric integration into a rational function integration. And when dealing with integration by integration of rational function, we need to make sure that we look at the degree of the polynomial, right? The polynomial that we see here, or the rational function that we see. So we see that now the degree of the numerator is less than the degree of the denominator. So we will think about that, and we will try to see that whether the denominator is factorizable. So we see that, oh, actually it's doable, right? So I think most students, they have learned it from their MYP as well. So we can factorize it. So it'll be u minus 2, u plus 1. So we can factorize the denominator completely, right, by doing it, right? And then so we, after we look at the fraction here, so it involves the second technique, right, which is the uh, partial fraction. So what's partial fraction? We define, right? We define u over u minus 2, u plus 1 as we want to split the combined algebraic fraction back into a single term, separate two terms. That's the meaning of partial fraction. And it's a very essential skill when we are dealing with the integration of rational function. Whenever we see a factorizable denominator with degree 2, or degree, like, as long as like it's a product of two function, right? You can factorize it into two linear or non-linear function. You can try to split it by doing the partial fraction. So you can split to a over u minus 2. We define, right? We want to break it back before we combine into the algebraic fraction. So we try to split it, and we define a and b as a constant here because we don't know what will be the constant to make them go backward. So we try to solve a and b. Okay, so we try to take the same denominator on both sides. Okay, so that makes sense. That makes sense. And then so afterwards, right, we could quickly obtain this relationship and we want to figure out A and B. So here we have a few methods, right, that can employ to solve A and B. But the fastest way that we should employ, right, the quick trick, right, that we can do is like we can take, right, for example, we take U to be -1. Why? Some say, oh, why do we take U to be 10? Okay, no, we won't do it, right? Why? Because if you take U to be -1, right, you make this term to be 0, right? Think about it, right? -1 plus 1 is 0. So actually, whenever you have this expression, right, like left hand side, right hand side, you can always plug in a number that work, right? That work perfectly. So of course, we don't pick the number randomly. Usually we pick some smart number. The smart number that we pick with -1 here. So the left side will be -1. The right side will be, this one is 0, right? And then this one will be -3. So we know that B is actually 1/3, right? Similarly, right, we take U to be 2. If you take U to be 2, so this guy will go 0. You can imagine that, right? So now we eliminate B, right? And then we want A, right? That's what we want, right? So the left side with 2, and then A times 3. 2 plus 1 is 3, right? So, and then we know that A is actually 2/3, right? 2/3, the solving the equation. So now the integration of the rational part will become easier because we can turn the integration of the U minus 2, U plus 1, du into two part. So it's 2/3 over U minus 2, du, plus, we can split it, 1/3, U plus 1, du. So that's what we need, right? That's what we need. And based on some property, we know that, right? Actually, the constant can be taken out of the integration because it's independent. So it's 2/3. And we would do a linear transformation here. So we can discuss the detail of the trick more in class, of course, right? But when we are dealing with like U minus 2, so we can always try to subtract a constant or add a constant at the back. So it's like doable. Okay, it's legal to do it. Okay, in integration. Uh, uh. So you may ask, okay, why? Okay, or if you ask why, then okay, you definitely need a class with me. Okay, we'll see you in the classroom. Okay. The 1/3 can go out. We can take out the 1/3 again. So we can do the same trick again. So we can modify the differential at the back to U plus 1. This is actually doable, and if you recognize it, actually this is like 1 over something. The same thing, right? Which is ln. So we can finish the integration by doing ln absolute U minus 2 plus 1/3 absolute U plus 1. Don't forget that you need to add a constant C at the back after you finish the integration because this is indefinite integration. For definite, you don't need to do it, right? Okay. So something will stop here and then you will lose 1 point because our focus is not U, right? Because remember, this is a substitution, right? Remember, we plug in U as sine X, right? So that means finally we need to do we call it back substitution. We go backward and this is sine X minus 2. And this is, oh, sorry, I forget to write ln here. I missed the ln, sorry. Okay, ln, and then that will be sine X plus 1. And then we add C here. So that would be the answer, right? That's you can do further simplification if you want, but it won't be necessary. Actually, if you don't, it won't be necessary. Actually, they will give you everything for the exam board. So basically that's the solution of the whole question. So why don't we just give a quick recall on what we did, right? So first of all, right, this is a question of trigonometry, but because we don't know how to do it, or the question just asked you to do a substitution, so we asked you to do so, so we just follow. And then the first trick that come here will be like, the first trick that come here will be this one. So we need to, after you do substitution, you need to do differentiation. You need to differentiate it, and then you need to change the category of the trigonometry integration into a rational function integration. We can see that, right? So, and then the second trick comes here will be this one, the partial fraction. The partial fraction process, which is very essential. You need partial fraction to finish the integration of the rational function. So we factorize it and then we define it, and then we apply a very special trick here. We just use numbers to plug in to the relationship to get A and B instead of doing something called the comparing coefficients, which is not smart, which is not smart, okay? You can do it, okay? I would appreciate it as well if you try it out, but definitely we would try to use some special numbers, and it will definitely give us a very quick result, okay? And then afterwards, right, we try to plug in the results of A and B, and we can split the rational function into two integrable function. And the final trick here is like we do a linear transform. It's linear transformation, like on the integral to make it work. Okay, so we can always add constant, subtract constant, and there are a few shortcuts that is doable. And finally, right, don't forget that we do a back substitution here. Okay, going back finally. Don't just stop at the stage of U, right? Otherwise, you will get 1 point deducted from the exam board. Okay, so that will be my presentation of today. Thank you very much for your attention. I hope that it will be really helpful. The teach something serious will be helpful to you guys, and if you figure out that it's really helpful and you want to encourage us, right, as we encourage Arch, right, to do more, definitely comment to give comments to Arch, and then we can definitely make more videos in the future and discuss the solution in detail, right? Sometimes if you read the marking scheme, it may not be helpful as well, right? So sometimes we need video to help, okay? So that will be it. Thank you very much. See you guys in the classroom. Okay, bye.